And this work is based on a paper we recently published in Nature Communications, Earth and Environment. So the motivation for this work is to enable consistent economic transition risk analysis and also physical climate risk analysis. Economists are interested in many more emissions pathways that we simulate in the CMIP exercises, but they require CMIP-like data to assess climate-induced population impacts, climate damage functions associated with labour productivity and reduction in agricultural production. So we developed QuickClim. So QuickClim, after ingesting all of the available CMIP5 data, we're now able to reconstruct CMIP5 projections associated with any emissions pathway you so desire, and for any climate monthly average surface variables that you require as well. So how do we do this? Essentially 4 parts to it. First is a model reduction step, where we extract the climate change component in the underlying data. Next is the training step, where we're learning the relationship between the carbon equivalent concentrations of each scenario and its associated climate change response. And then the projection, so we're applying these models to create a projection of this climate change response for the emissions pathway it hasn't seen. And then we convert this time series back into gridded fields and introduce a climate variability component. So I'll step through how each of these parts work. First is the model reduction part. Here I'm illustrating just for surface air temperature, but it's a multivariate approach. We can reconstruct many variables all at one hit, but for simplicity, I'm just going to show you how we do it for surface air temperature. The trick here is you effectively have to concatenate together all of the different scenarios into one metadata set. And then you calculate climatological averages across all scenarios and all time, and climatological standard deviations, and then you normalize your data set by these climatological quantities. You then calculate the EOF decomposition of this standardized data set, and the first EOF is systematically the climate change component. It's because the greatest distinction across all of these data sets is the scenario itself. And then this one pattern is associated with the scenario-dependent principal components, and this is the only principal component of all of them that have any trends in them and that have any relationship with the emissions. All of the other principal components are associated with climate variability. So now the task of learning how the emissions influence the climate is one simplified down to how do the emissions influence these 3 principal components. Because all of these time series have trends, we can't use standard time series analysis methods. So we're using a finite element method, bounded variation, vector order regressive model with exogenous factors. It's a long acronym. But essentially, because we have time series with trends, the way that we deal with that is we chop our time series up into finite elements or local time chunks and treat each local time chunk as being statistically stationary. And we learn a vector order regressive model for each time chunk. So we have multiple vector order regressive models which are switching from chunk to chunk. And we learn the coefficients in the vector order regressive models and also the instances in time when we're switching. I'll show you what the model looks like, maybe a bit more clearer. So essentially our x of t are our principal component. We do this for each scenario separately. It's modeled by a constant offset plus coefficient multiplying itself by the time series of previous instances in time. That's the vector order regressive part. And then we have another coefficient b, which is effectively the climate sensitivity of the model it's trying to represent, multiplied by u, which is, where's my cursor going? The carbon equivalent concentrations. And the superscript i's are because we have multiple vector order regressive models that are switching from one to the next. So the way these models look, what these models look like, again, we've done this for each scenario. So for RCP 2.6, this particular representation has 2 vector order regressive models, or 2 clusters. Each of them have slightly different coefficients and slightly different climate sensitivities. And then we have an associated affiliation sequence, which is just turning on and off the appropriate vector order regressive model at the appropriate time. And this is how we deal with non-stationarity in the data. So using these vector order regressive representations and the associated affiliation sequences, if we start from the initial conditions or the very first value of these principal components, and then run these time series models forward in time, we can reconstruct RCP 2.6, 4.5, and 8.5. Now that in itself isn't all that impressive, it's just reconstructing the data from which it was learnt. But now that we have these representations, we can see if we can use our RCP 4.5 model and our RCP 2.6 model to reconstruct RCP 8.5 and 2.6 to reconstruct RCP 4.5. So the way that we do that, you might recall on the previous slide, we've got these terms here, the U of T's. So the U of T's, that's the radiative forcing, essentially, the carbon equivalent concentrations. So in doing this red line, or the RCP 8.5 projection, it used the RCP 8.5 carbon equivalent emissions. So if we pull out those carbon equivalent emissions and replace it with the carbon equivalent emissions for RCP 4.5, then that red line drops down from where it was originally down to here. And likewise, when we do so for the RCP 2.6 case, we're replacing its carbon equivalent emissions with the carbon equivalent emissions for RCP 4.5, and it's lifted to where it was to, centered around about where RCP 4.5 is. And we can quantify the distance at which these time series have been shifted. So logically, you would think the further a particular model has deviated from the data it was originally learnt on, the less trustworthy it is. So we can calculate error measures based on how far these models have deviated, so the red line and the blue line here. And on the basis of these errors, we can calculate a set of weights, which is over here. So we would kind of weight the blue model, or the RCP 2.6 model, more heavily than we would weight the RCP 8.5 model, because RCP 2.6 is closer to RCP 4.5. So we can use this time-varying set of weights to, in a time-varying sense, combine the model coefficients that we've learned for RCP 8.5 and RCP 2.6, and that produces a RCP 4.5-like set of model coefficients, which we then run forward using the RCP 4.5 carbon equivalent emissions. And that gives us the purple line. So the moral of the story is we can reconstruct the line in the middle. Right? So you might say, well, that's an easy case. Using the top case and the bottom case to reconstruct something in the middle is like interpolation, which is true. But we've also used the top two to reconstruct the bottom one, and the bottom two to reconstruct the top one, and it's all equally valid. So that's all based on trying to reconstruct the climate change component. And if you recall, we had that red EOF pattern, that's the spatially defined climate change response. So if we multiply that time series by that spatial pattern, we get a spatio-temporally evolving climate change component. And then we have a conditional sampling approach to which we reintroduce the climate variability part, which we can go through in question time if you're interested. And so then the new, thanks Rachel, the new time series is just the climate change part plus the climate variability part, which is still standardized, but we dimensionalize it by multiplying it by the climatological standard deviation that we calculated at the very beginning, and then adding on the climatological average. Now, we've done a bunch of validation comparing the RCP 4.5 time average and standard deviations to the associated reconstructions, so we get very high pattern correlations, and also done comparisons based on time series measures, globally average surface air temperatures, PDFs and autocorrelation functions of Niño indices. And we've also done so across the full CMIP5 ensemble, and these box plots are just showing that all models are reasonably well reconstructed. So now that we've got this approach and we can generate these reconstructions and really fast, we can do many of these emissions pathways. So here we've got 100 different magenta lines, so 100 different emissions pathways. We have 15 models for each, 15 CMIP models for each pathway, and so we've reconstructed 100 pathways by 15 models by 100 years, so it's about 150,000 model years of data, which we can do in an hour on a laptop. And then now that we've got many emissions pathways, we can look at statistics across the emissions pathway. So what's the 5th percentile of warming in the year 2090? What's the 95th minus the 5th percentile? And same for anomalous standard deviation, skewness, kurtosis, all of those types of quantities. So here, this is like a standard type of case study, but we've also done so for the sensitivity of the trajectory toward net zero emissions type pathways. That's me telling you that my time is up. Yeah, so just moving on to concluding remarks. In summary, QuickClim uses CMIP data to generate spatially, temporally, time-evolving data sets for user-defined sets of climate variables and also user-defined sets of arbitrary emissions pathways. The learning process for a given model takes about 20 minutes on a laptop, and a century-long projection can be done in seconds. And this enables a consistent economic and physical risk assessment. In terms of its relationship with other modelling efforts, QuickClim is not intended to replace CMIP models at all. It doesn't exist without CMIP model data. And also, it's the post-processing of QuickClim output should just slot seamlessly into the post-processing of CMIP model output. It's got the same grid, same variable names. And the code's on Zenodo. All the links are in the paper, so if you want to download it, play with it, break it, be my guest. In terms of the limitations, QuickClim aims to reproduce what CMIP models do, not what the climate does. So any model biases or deficiencies that are in the CMIP models are also in the QuickClim reconstruction of those models. I'll present an alternate approach tomorrow during our ML working group meeting on doing this from reanalysis, which is kind of a slightly different take on it. Thank you.
It'd be pretty cool to use this for testing evaluation tools and all this stuff, because you don't have to have a bunch of data lying around. You can just generate it.
Yeah.
Deterministically.
Yeah, good call.
One thing I didn't understand, you say for a user-defined set of variables.
Yeah.
So are each of those variables independent of each other in QuickClim?
So as long as those variables exist in the CMIP archive for a particular model, then QuickClim can reconstruct it. So say the ACCESS model has surface air temperature, relative humidity, rainfall, mean sea level pressure for 3 different emissions pathways. QuickClim can reconstruct those.
But does QuickClim know that when it's doing the learning about the temperature data, does it leverage off the humidity at all, or does it do that independently?
Well, okay. The trick is redefining the EOF, right? So the absolute necessity is that you need surface air temperature, because that's the one that has the strong relationship with the carbon equivalent emissions. So if you want to look at reconstruct other variables, then those other variables are kind of tacked onto your inner product of how you calculate your EOF. But importantly, they're divided by the number of additional variables. So I did this in a naive way the first time. I just tacked on 10 variables, and then very quickly you lose the relationship to the carbon equivalent emissions because rainfall and all these other things aren't strongly related to it. But when you do it this way, the relationship between the temperature and the carbon equivalent emissions is retained, and the component of all of those other variables that co-varies with temperature is kind of dragged along with it. So that's the approach.
Right. So we have Martin and then Pierce.
Where are you getting the aerosol component of the radiative forcing from?
So in CMIP 5, the carbon equivalent emissions is provided, right? Yeah. So if we were to do this with CMIP 6, we would need to, as you're alluding to, we would need to calculate an effective carbon equivalent concentration, which I think you can do with magic, presumably. Yeah. I wanted to try and get away from prescribing a model-dependent carbon equivalent emissions, because I wanted to diagnose what the climate sensitivity was. I didn't want to prescribe that, to kind of preserve the diversity across the ensemble.
Yes.
Hi, you showed an example, which I guess was your simplest example of there being 2 phases or 2 oscillations.
Yes. Two different clusters.
Exactly. Yeah. But I can imagine there being many. So are the number of phases, I'm just calling them phases, is the number of phases, are they related to the number of modes of internal variability that affect the variable?
I would say it's more of a hyperparameter. So I didn't discuss that and kind of brushed over it, but there's 3 hyperparameters essentially. The number of clusters or number of different vector autoregressive models, how far back in time you need to go in your vector autoregressive model, essentially M, how many months ago is important, and the persistence or how often you allow the switching. So you kind of need to systematically test all full factorial combinations of these hyperparameters. And so you pick the one that best fits the data, but also with not an excessive number of parameters as well. So I would say, at least my decision on these parameters being based more on out-of-sample fitting to the data rather than like a physical explanation that you're kind of alluding to.
Okay, okay. Thanks.
Right.